For our next section, we're going to be talking about the different temperature scales. So our aims for section 2.7 are to learn the three temperature scales and then to be able to convert from one scale to another. We'll use two of these scales a lot more often than the rest of them, so I'm not going to require too much conversion between Fahrenheit, for example, and Celsius or Kelvin, but we do use Celsius and Kelvin fairly frequently. So we've got the three different scales. We've got Celsius, which I'm sure we've heard of. Fahrenheit, we use a little bit more. And Kelvin, we've probably not heard of quite so much. So we start with the freezing and boiling temperatures in terms of water in Celsius degrees. So we know that water freezes at 0 degrees Celsius. And anytime you see this written, you'll see a degrees Celsius symbol next to it. We know water boils at 100 degrees Celsius. This makes the Celsius scale really easy to remember. 0 is freezing, 100 is boiling. The next scale we want to look at is something that we use more often here in America, and that's the Fahrenheit scale. The Fahrenheit scale is named for Daniel Gilbert Fahrenheit, and he actually started experimenting with the freezing and boiling temperatures of brine. And brine, you may or may not already know, is salt water. So you can already see why it's not really handy for us to use. We don't use brine really in everyday life. So there's no reason for us to really know when it freezes and when it boils in terms of temperature. But this freezing temperature we're very familiar with. This is the one we look for to know whether or not school is going to be canceled. And this ends up being 32, and we will also see a degree Fahrenheit symbol where water freezes. Water boils is a much more uncommon temperature in terms of Fahrenheit, but this is 212 degrees Fahrenheit. So you can see already it's not a nice clean transition between Celsius and Fahrenheit. The Kelvin scale is what we should be using, and Kelvin scale is based on the temperature, the freezing and boiling temperatures of gases, or rather the properties of gases. We know that water freezes at 273 Kelvin, and we know that water boils at 373 Kelvin. These are not referred to as degrees. They're just referred to as the temperature in Kelvin. So you can see there's not a really nice transition between Celsius and Fahrenheit, or even between Fahrenheit and Kelvin. But if we're looking at the difference between Celsius and Kelvin, it should be very clear that the same jump between the freezing temperature of Celsius and Kelvin, which we can see here and here, is 273 degrees, is the same jump between the boiling temperature of water in Celsius and Kelvin. So again, a 273 difference. This makes it very easy to convert between the scales. So we can see here again a comparison between all of the different temperatures. We can see that water freezes at the temperatures we just talked about. And depending on your source, you might see a slightly different value for the freezing temperature in Kelvin. We just use 273. It's easier to remember, but 273.15 is also acceptable. So we just talked about this 273.15, 0 Celsius, and then 32 Fahrenheit for freezing temperatures, and that's at sea level. And we'll talk about when we're not at sea level in a later chapter. You can see body temperature, just for comparison purposes. We have right around 310 Kelvin in the range of 40 Celsius and 95 to 100, and we know that as about 98.7 degrees Fahrenheit for body temperature. We also just talked about where water boils, and we can see again that's 373 or 373.15 in Kelvin, 100 in Celsius, and 212 in Fahrenheit. Absolute zero is something we're going to talk about in just a minute, but the important part here is to note that absolute zero refers to 0 Kelvin. So we have a little cartoon here where what's happening is we're at 0 Kelvin, which is the equivalent of negative 273.15 degrees Celsius, which is also the equivalent of negative 459.67 degrees Fahrenheit. And what we know at this temperature is that when we do have a temperature that's close to 0 Kelvin, we know all particle motion stops, and we can see what's happening in this cartoon right here. He's saying, so cold, I'm not even vibrating or shaking. So remember what temperature actually is. It's a measure of the kinetic energy of the particles. So if we're at 0 Kelvin, that means we're not registering any sort of temperature. We're not registering any temperature at all, which means those particles, those molecules can't even be moving enough to generate any sort of heat at all. So not even vibrating or shaking. Theoretically, matter ceases to exist at that point. We have not quite reached 0 Kelvin. We've come very close, within about a billionth of a degree, but we can't quite get there.
So if we're thinking about why we can't reach absolute zero, if we think about what's happening when we probe a sample, we're actually introducing a small amount of energy to that sample just by putting other particles that are vibrating in the vicinity of whatever it is that we're measuring. We're actually introducing some heat to that sample. So our probe itself would be supplying a small amount of energy to whatever sample we're trying to get down to absolute zero. So that's why it's just a theoretical temperature at this point. It's very hard to completely remove all kinetic energy or all energy of particle movement from a system and still be able to have it reach absolute zero.
If we're converting from one temperature scale to another, for example, converting from 70 degrees Celsius to Kelvin, we talked about the difference on those scales and how it was very easy to convert from one scale to another. So if we're converting from Celsius to Kelvin, we use this formula. We saw back at that table that there was a 273-degree difference between the Celsius and Kelvin scale. So we know that what we have to do is start in degrees Celsius, and our given value was 70. So that's where we're starting here. 70 degrees Celsius, and we are adding 273. This will give us our value in Kelvin. Remember, we're not saying degrees Kelvin, we just say Kelvin. So if we take 70 and we add 273, we get 343 Kelvin. For the next example, if I have 77 Kelvin and I'm asked to convert that to degrees Celsius, I know that the Celsius temperature can be reached by starting with Kelvin and subtracting 273. So 77 Kelvin minus 273 is negative 196 degrees Celsius. We know this value makes sense if we see a negative value in degrees Celsius. What we also need to remember is that we cannot have a negative value for Kelvin, because remember, the lowest theoretical temperature that can be reached is 0 Kelvin. So therefore, we cannot have negative values. If you get a negative value for the temperature in Kelvin, you've done something wrong, probably subtracted when you should have added. So just keep that in mind. Negative Kelvin temperatures do not exist. Now we're going to look at converting Celsius to Fahrenheit. This is where it gets a little bit messy. So we've seen that we can do this in one step, maybe in previous science classes, but it might be easier to do it in several steps. What we're looking at here is taking our value in degrees Celsius and we're multiplying it by 1.8 and then adding 32. So like I said, this gets messy. This would be an example of an extension question that you would have to do for A level. This is beyond what I expect you to know for this class. So 1.80 times 28 plus 32 gives us our temperature in degrees Fahrenheit, which is 82.4 degrees Fahrenheit. And the last example looks at converting Fahrenheit to Celsius. So we can do this by reversing the process that we just looked at, starting with our temperature in degrees Fahrenheit, which in this case is 38. We're going to subtract 32 and then divide by 1.80. So remember, if this part is on top, if it's in the numerator, we need parentheses around there to remind us to do that part first. So plugging in our starting value for degrees Fahrenheit, we have 38 degrees Fahrenheit. We're going to subtract 32 in parentheses, divide by 1.80, and we get our temperature in degrees Celsius, which turns out to be 3.3 degrees Celsius. If you think about this conceptually, it makes sense. We know 32 degrees Fahrenheit is near freezing. So if we get a temperature that's 3.3 degrees Celsius, That's also near freezing on the Celsius scale. So we did something right when we can compare the two temperatures and they represent something very similar. Now, if I want to go one step further and I want to convert this Celsius temperature to Kelvin, I can just apply what I know about changing Celsius to Kelvin, which means we just add 273. So I'm going to take that temperature I just calculated, 3.3 degrees Celsius, and I'm going to add 273 to turn that value into Kelvin. And that means I get 276.3. It's easier to do this in multiple steps than it is to look at the entire equation in one step. But if you prefer to do it that way, going back to the equation we saw here, we would just have to remember that this additional piece gets in parentheses, and then we're going to be adding 273 to the end. How you choose to do it is up to you, but it might be easier for you to view it in two steps rather than one.